understand that what is class A, class B, class C amplifier, we have to learn first of all what is a load line and how it can be drawn. And to understand the load line, we have to learn first of all a parameter which is beta. Okay, beta is a current gain for common emitter configuration. So this is, like emitter is grounded, collector and base is input, collector is output, and emitter is grounded. Okay, so then beta is defined as output current upon input current, that is IC upon IP, output current over the input current. This is a circuit for common emitter configuration. Here the base current is 200 microampere. Okay, and then we will find now what is collector current flowing. Let beta is equals to 50. Let we say it is 50, and it may have any value otherwise. 50 into 200 microampere. So it becomes 10,000 microampere. 10,000 microampere means 10 milliampere. So collector current is, this is collector current along y-axis, and it is our 10 milliampere. And base current is 200 microampere, which is fixed. Okay, and along x-axis in the graph it is collector emitter voltage. So how we find collector emitter voltage? This is a formula. VCE equals to VCC, which is 10 volt, minus IC into RC. RC is in the figure, it is 220 ohm. Okay, so this is IC, 10 milliampere into 220 ohm, and milliampere into ohm becomes millivolt. So it is 220 and 00 millivolt, and 2200 millivolt means 2.2 volt. So it becomes 7.8 volt. This is VCE. It is here. Okay, VCE. So because along x-axis it is VCE. Now in our figure VCE is fixed 7.8 volt. So here it is 7.8. Collector current is 10 milliampere. Base current is 200 microampere. These are the parameters for this figure. Now in this figure IB is increased 200 to 300 microampere. So IB is increased, that means IC will also increase. So just looking here, it becomes 15,000 microampere, and 15,000 mean 15 milliampere. So this is the value of 15 milliampere. So this is our collector current. First it was 10, now it is 15. So it is increased collector current. So collector current is 15 milliampere. Now the thing is, what is VCE? The voltage across collector and emitter. The same formula as was applied before. Now substituting the values. So it becomes now 6.7 volt. Now one thing to be noted, with the increase in IP, IC, VCE is not increasing, it is decreased. First it was 7.8 volt, now it is 6.7 volt. So VCE is decreased. So as explained just before, VCE is 6.7 volt, IC is 15 milliampere, it is 300 microampere. Now IB is further increased 300 to 400 microampere, with the result IC further increases. Now it becomes from 15 to 20 milliampere. So with the result, now the question is, what happens to VCE, collector emitter voltage? So applying the same formula, so it becomes, applying the same formula, it becomes 5.6 volt. Again, this is very important. The VC is further decreased. First it was 6.7, now it is only 5.6 volt. So with increase in IB, IC, it is important that VCE is decreasing. Okay, this is to remember. So, as I explained with the numerical values, that VCE and IC, they are reciprocal. As IC increases, VC go on decreasing. So that's the Q points. You know, like IC is 10, 15, 20. VCE decreasing 7.8 was 8, 6.7 volt then. Now it is 5.6 volts, so it is decreasing. So that's why the load line is with the negative slope. Okay, this is a load line with negative slope. It is showing that VCE and IC, they are in reciprocal. Okay, so this line is called the load line. So how we draw this load line? Simple. We were having three values, like with 10 milliampere, the VCE was 7.8 volt. With 15 it was 6.7 volt. With 20 milliampere it was 5.6 volt. 3 points were chosen. 3 points are chosen and marked on the area between VCE and IC. Then joining the 3 points Q1, Q2, Q3, that becomes the load line. Now this is a circuit showing about, this is the input signal which is varying about 300 microampere. Okay, with this VB is fixed reference voltage and input signal is varying about the reference. So collector current is varying in same way, but the collector emitter voltage is reciprocal. Increase in, IC, VCE, it is in a decreasing trend then. So it is decreasing like this VCE. Okay, and then with this part of the collector current, okay, negative part, because of the base current is negative mean decreased. So collector current is other way around, it is increased. So the faithful reproduction of the signal, there is no distortion if the Q point lies in between the load line, at the center of the load line, you can say. If Q point is at the center, at the center, then there is a faithful reproduction of the input signal. There is no distortion. Only one thing is that without input signal, there is some base current, a reasonable amount of base current, it flows, which is again a limitation of the circuit. So looking to this figure here, Q point node at the center, it is somewhat higher. So input signal is swinging. This is a part of the signal which is and now it goes to saturate, it is cut, and there is no reproduction of this part because collector current becomes saturate for this part. Okay, so here the collector current becomes saturate, but for rest of the signal, input signal, there is collector current, and here collector emitter voltage is same way, some part is cut. So the rest of the part it is okay. So transistor is driven into saturation because the Q point is too close to the saturation for the given input signal. Okay, so some part is looking to this figure here, Q point is too close to cutoff. So input signal no problem here, output is there, but for this part some signal is cut because it is going in a cutoff region. So some part of the signal it is cut. Okay, so this part is cut. Similarly, collector emitter voltage, some part goes. Now here there is a problem that input signal is very large, but the Q point here, the Q point is at the center of the line, no problem, but the signal is very, input signal is large. So what happened then? If the input signal is large, this portion goes to saturate, this portion becomes saturate. Okay, and this is exactly in the same way the collector emitter voltage, some part is cut. So here again some portion is it is going to cut off. Similarly, collector emitter voltage, some part is going to cut off, and similarly the collector emitter voltage likewise. So the signal is clipped from the both sides because it is going to saturation and cut off because input signal is large, but Q point is again it is at the center even then. This is class A amplifier. Class A amplifier means this is input signal is varying like this. Q point is at the center, and we will get output it here, and this is exactly reproduction of the output signal. There is no distortion, but the problem in class A amplifier is because Q point is center, so some base current always flows without even the input signal, and this becomes the limitation of the circuit for its efficiency, because without input signal some base current is flowing. Okay, but the signal is exactly reproduced. So this is a circuit, and for class B amplifier, this is a load line. Q point, is touching to the collector emitter voltage excess, with the result that without the input signal, there is no base current flowing through the transistor. This is better for the efficiency, okay? Now, the input signal is varying. This is input signal. It is varying like this. Okay. Then, output signal. And for this part of the input signal, there is no crossed, no output signal. And for this part, the output signal, it appears like this. So there is output only for one half. One half is clipped. So the two transistors, emitter common. One is NP and other is PNP. Emitter are made common. Input signal, and it is broken by the two transistors. One transistor handles only the one half of the signal. Okay, like this half is handled by the upper transistor, and second part is handled by the other transistors. Other transistor means the lower transistor. There's a push-pull arrangement, that again we get the ultimately in the output the full signal, but one transistor handles the half one. So the positive point is, the application is, with this the efficiency becomes better. So this is a class B amplifier. This is a circuit for class AB amplifier, having both the properties of class A as well as class B, right? Now here the Q point is lying, Q point is at here. It is not touching to collector emitter voltage axis, and it is not at the midpoint. It is not midpoint like class A, and it is not touching to collector emitter voltage axis like the class B, but it is near the near to this axis. So what happens if the input signal is varying like this? For input signal, the variation of the input signal, this part, only this part from here to here, and from here to here, this part and this part, it appears like this part and this part, and this part is clipped, and rest of the signal for this part, it is appearing. So it is appearing like this. So this is a circuit diagram. So in the absence of this signal, some base current flows, very small. That's why the Q point is here. But even then, the efficiency is better, because not appreciable amount of base current flowing without input signal. class C amplifier is so biased that output current is 0 for more than 1/2 of the input sinusoidal signal. Okay, and there's a reason that eta efficiency of this amplifier is very large. This is a load line, right? And this is a Q point. It is far down. The collector emitter voltage excess. Okay. Now the output appears only for this part of the signal. Okay, this part of the signal, it appears here like this, and rest of the signal, rest of the signal is cleared. A part of the signal is appeared. Now we'll find the efficiency of class B amplifier, and keeping in mind that in class B amplifier the output appears only for 1/2 of the input signal. So this is a load line. Okay, this is a Q point. Along x-axis it is collector emitter voltage, and maximum collector emitter voltage is equals to, at the Q point, it is equals to VCC. Along y-axis it is the collector current. So now the collector emitter voltage varies because of the variation in the voltage of the input signal. So input signal makes the collector emitter voltage to swing like this. Okay. Now one thing keep in mind that as this voltage is going to more negative, so collector current is the reciprocal of it, then collector current will increase, and when it is going to increase, when collector emitter voltage is going to increase, then collector current will come down. Now when collector emitter voltage is becoming more positive, because the Q point maximum voltage is here VCC, and it is going to more increase, but it is a limitation that collector current cannot increase further, because collector current is a reciprocal of it. As it is increasing further, collector current cannot increase. Okay, so there is no collector current now. There will be no collector current for this part. Again the collector current now, it will start, because it is going to more negative, the collector current will start increasing, and when it is increasing, the collector current will come down. Okay. Now we will find what is the average current flowing in the output, because only one half of the signal is appeared at the output. So the total voltage of the one half cycle is calculated from 0 to pi, because pi to 2 pi there is no cycle. But we have to divide this total by 2 pi for making the average current. Okay, from 0 to 2 pi the average current is the numerator, total voltage 0 to pi divided by 2 pi. Okay. Rest of the mathematics is very simple. You just follow the steps and you will find it. Now you know that there is a relation between RMS root mean square value of current with the peak value of the current, that it is peak value of current divided by root 2, that becomes the RMS current. Similarly, the RMS voltage you can find by using the same type of relation. So this efficiency is very good, 78.5%. Okay,